All right, everyone. Welcome to another episode of Robo Papers. Super happy today to have Wenli, one of the co-authors of this paper called Self-Improving Vision Language Action Models with Data Generation via Residual RL. I think PLD for short, maybe?
Yeah.
Something like that. Okay, PLD for sure. I'm very happy to have Wenli. I was just telling Wenli, like, this is one of the maybe best papers I've read like in a while. Really, really impressive stuff. So really looking for. Sorry to say, maybe okay. Don't want to give you too much
No
pressure,
pressure, though,
but
so.
yeah, really looking forward to your sharing. I think some really neat ideas and really neat results here. But maybe as a start, if you can share with us about yourself and before we dive in.
Okay. Thanks for having me. I'm Wenli. I'm currently a PhD student at Carnegie Mellon University, working with Professor Guanya. And this work actually comes out from the internship I did at NVIDIA Gear Lab. And actually, I've been doing long-term internship at Gear Lab since last year. And I see a lot of progress, like from the perspective of industry frontier research lab. And the idea of this paper actually comes from some of the thoughts, like for my research and my thoughts of observing the progress of the entire area of robot learning. Yeah, and I'd like to share some of my insights in the podcast.
Awesome, cool.
Yeah.
So
okay.
what are we seeing here?
This is a teaser about the actual performance of our method.
So it's doing GPU
this
insertion.
This is just a continuous non-cut video that show like 24 cycles of insertion GPU and like unplug it, insert to another slot, and go back and forth.
How many GPUs did you break while training this?
That was my first question to you just now.
Sorry, how many GPUs did you break while training this?
Actually, no GPU is being hurt in this process.
Okay.
But you can see there's actually should have some buckets on the slot, but we broke that.
The little tabs
during the RL.
Right.
Yeah. So that's basically the teaser video.
And so this is
basically
this is
really
like a real high tolerance task, right? It's nice. Very cool.
Yeah. Actually, there are something very interesting and painful about the demo. That is, I spent about 8 hours just sitting like beside the YAMM setup and watch it like do reinforcement learning. And this is so painful. But thank God the performance is good.
So I'm sure you get to this, but like, can you tell us about the reinforcement learning setup a bit, or what? Would be the
Sure.
Yeah.
So our method.
Well, also feel free to go in order instead if you'd rather. We can get to it later.
Okay. So let's have a quick overview about our method. So our method has 3 stages. The first is about the real-world reinforcement learning part. And the second is data collection. And the third is distillation. And these are like correspond to the probe, learn, distill. But actually, it's learn, probe, distill. So the first part is learning. So here we want to build like post-training API that can take in any VLA model or like robot foundation policy model to the pipeline, and we do some rounds of learning, and we give you back a very good policy, like high 99 success rate. So to achieve that, we didn't like exploit the policy architecture of the VLA model. There's diffusion head, there's autoregressive head. So we just treat them as just PyVLA and don't touch that part and train a residual RL on top of it. So in practice, it's just it has the same action space with the VLA model. It's a like VLA output plus some delta term, and we can go into the RL details later. And here the basic idea is like we do off policy RL, like we have some data buffers and flood in the buffer and do policy updates. Like after 8 hours, you can learn a GPU insertion skill. And that's for the first part. And for the second one, I think that's very important. And one of the important idea we want to sell from our paper, that is probing. like aka like hybrid data collection. When we do, wait a minute, I have a very nice figure to show. Yeah, here. So, so for currently for most of the foundation models, if you really want to deploy that for specific task, you have to do SFT, right? So that is you download the Pi0 model or GROOT model and you collect 20 trajectories in your own robot and do SFT. And then it has some success rate. And we actually treat this as a very good baseline. And we find the data collected by human is not good enough because you may shake your hand while collecting data and the trajectory may not be optimal. So like researchers from UC Berkeley, they have a paper called RLDG. They use real-world reinforcement learning to collect rollouts and use RL data to do the SFT. And we find this is also not very good because the RL data is too optimal. So you can see in the middle, the trajectory is generated by RL is concentrated to the optimal trajectory. So the problem is when you distill this data back to the VLA, there's kind of a collapse for the action distribution. Although we didn't visualize that, we observe that in the experiment results. That is, once a robot moves to the OOD state, it's not able to recover. So that is an important counterintuitive part. That is, using RL data cannot actually improve the VLA performance. So we try to do some combination, and we want both optimal and recoverable trajectories. That is our PLD trajectory. So what we did is we just, for the policy rollout, for the first section of the rollout, we just use the base policy. And it will drive the robot to some random but recoverable state. And then we switch back to RL. So for the remaining part of the trajectory is optimal. So with this method, we can collect very diverse and optimal trajectory to our data set. And we use that data to do SFT. The performance will be very good.
How do you know a particular action from the base policy is going to be recoverable?
So that's a very good question. That is related to our RL training. So when training the residual RL training, we also do conduct this process for the first few steps of the trajectory. We just use base policy to roll out and then switch back to residual RL. So during the training process, the state base is well covered. So the RL can drive the arm back even it's in some random state. And that's actually a good question. There's no guarantee. If we are going to some irrecoverable state, then we have no idea what to do. But in practice, we didn't encounter that.
This is partly task design then too, because if it was something where the object could fall off the table or whatever.
Maybe. I think for our tabletop task, yeah.
Sorry, have you defined residual learning yet? Just for anyone.
Define residual learning.
What is the residual policy? Why did you choose to do this instead of fine-tuning the VLA or just doing reinforcement learning on the VLA, I guess?
Yeah. Oh, that's a very good question. We have thoughts about that. So we want the framework to be policy agnostic. So so we don't assume whether it's diffusion head or just transformer head. So I think doing residual RL is the most standard way to do that. If you want to just use RL to directly tune the policy, for different VLA architecture, you have different RL algorithm. And we didn't want to touch that in this project. And for another question, why not just do RL to tune VLA like how people did in VLM paradigm? That is because we assume it's low data regime. We have very limited budget of real world interaction. If we want to do GRPO for the VLA, we need a lot of trajectories, parallel rollouts, and I don't think current infrastructure supports that.
Okay, so the residual policy is then it's relatively small parameter count, and it's I forget what the exact number is, but and then 8 hours of data you were saying, so that's roughly how many trials I guess did it take to learn this, just to get a picture of how much data it takes.
Or we are doing 20 hertz control.
20 hertz control. Well, like I'm imagining.
It's about 500k.
Okay.
500k steps.
500k steps at 20 hertz, basically. Right?
Yeah, I think I think that's if we want to do GRPO, we need much more than that. Yeah, so that's why we do residual RL. And yeah, that's the second part. So this is actually very flexible. So here we bypass the need for learning for doing the multitask learning. We can just learn specialists for each of the tasks you are interested in and collect data for each of them. And after that, we just aggregate the model to a big data set and do standard SFT, like a LoRa fine-tuning for the VLA. And after that, we can just deploy the generalist to different tasks. Yeah. So that's a rough idea about the framework. And if you said you are interested in the RL part, so we can dive deeper into that. So for the RL part, it's also standard offline to online learning. So first of all, we can collect some offline trajectory by running the VLA policy rollout, because we assume the base model is not too bad. So we roll out the policy, it will have let's say 30 to 40% success rate, and we just only keep we keep all the trajectories and train and do CalQL offline RL training. After that, we can get warm up creating network, and then we move to online training part. Here we use RLPD, which is a off policy RL algorithm, and the idea of this algorithm is we have two data buffers, the online buffer and offline buffer, and we assume the offline buffer has very high quality. So here for the offline buffer, we throw out the failure trajectories, only keep the successful ones, and we do oversampling during the RL updates. So we sample 50% of the batch size from the online buffer and 50% from the offline buffer. And we do a SAC for the RL learning. And during the RL learning process, we keep flooding the online buffer, and after 8 hours, it can learn something. Yeah, so that's the basic idea of the RL algorithm. Yeah, it's quite standard, but there's one thing very important for all the residual RL algorithm, that is the action scale of the residual policy. So because we assume the base policy is good enough, it only needs intervention at some certain steps of the trajectory. So we want to keep the output of residual as small as possible. So we will add regularization for the action output. And here there's a visualization. We visualize the actual residual output during the trajectory. For example, here, yeah, you can see it will only have output at certain states. For example, here it's move the gripper to the right for a better pre-grasp position. And during the insertion part, you can see the base VLA policy will miss the perfect insertion position, so the RL will correct it, and eventually find the perfect match and do the insertion. And that's the idea of the residual policy.
So that's a very cool visualization. So you can see exactly that, it's making these tiny corrections just when it's needed, and it's usually flat. How sensitive is that regularization? How much tuning? Is it pretty generic? You can use the same setup for a bunch of tasks? I'm curious.
Oh, it's the same for a bunch of tasks. So you don't need very strong regularization. It's just a term with very small magnitude, small weight. Yeah, because the RL will learn not to intervene by itself eventually. Yeah, so that's about the method part. It's quite standard, and I think the most tricky part is to make real world RL actually works. You need a lot of design tricks. For example, how to tune the UTD update to data ratio, how to date the update frequency. That needs a lot of parameter tuning. So that's why it's very hard. And after the RL part, we actually did some very interesting study about the generalization, because we mentioned we do RL on specific some tasks and do the SFT, and we hope it to generalize to multiple tasks because the effort for RL is really huge. So we want to just train on small number of tasks and can generalize to a large number of scenarios in the real world. So we study whether this can happen because of the probing process of data collection. We assume the data set has already includes some recovery capability, and we wish this can be generalized to multiple tasks. So we did some study about that. So for this figure, it is we take the liberal 90 benchmark. There are 90 different tasks in the benchmark, and we only do RL training and data collection on a small portion of them and evaluate the entire 90 tasks. So you can see for the plot, the greener, the higher the success rate. We gradually increase the portion of data we used for training. Like for example, for this 10%, we only random pick 9 tasks from the benchmark, do real RL training, collect data, do SFT, and evaluate the remaining 90 tasks. And you can see as the training increase, the success rate of the overall evaluation increases. And from this figure, we can see that for this in distribution evaluation, the PLD data has comparable performance with the human data because for this benchmark, the human data are actually high quality. So you can imagine like training on human data, on this data and evaluation is kind of overfitting test. So you can see PLD data has comparable performance with human data. And for generalization, for this unseen OOD task, PLD data can actually outperform human data. And we think that comes from because we intentionally collect the recovered data set.
I'm having trouble understanding the plot here. Like, why? How should I read this? Okay. Why? How does this show that? Why is
Okay.
So I guess
Okay.
each vertical is 90 tasks, right? There are 90
Yeah.
boxes,
Okay.
something like that.
Okay.
Then so I assume, Wenli, correct me if I'm wrong. So the black color stuff is the tasks that is basically not trained. And so in theory, even if they are starting to turn slightly green, it suggests some generalizability.
Yeah, that's true.
Okay.
I see.
I see.
Okay.
Yeah,
So,
Whereas
so then,
when if it's sorry.
no, go ahead.
Whereas let's say if it's within, let's say at the 60%, portion, you would imagine it to, for those 60% of those 90 tasks, they should do well because you have given it like basically task specific demos, whether it's human or PLD, right? And so, yeah.
I see. So the fact that the bottom right one is almost all solid green means that on scene tasks, PLD is actually doing better, much better than the human data, or at least noticeably better, probably. Is that right? Because it's like actually 100%.
Yeah, and
Okay,
one thing we find interesting in this is for the leftmost plot, it's base policy rollout data, that is aka self bootstrapping. So what we did is we use human data to do SFT and roll out for those tasks and only keep the successful trajectories and use the successful trajectories to do the SFT again. And we find that because the modality of the policy is very narrow, so the model actually collapsed. Like even for some in-distribution evaluation, it shows very bad performance. So that's why we need the exploration by reinforcement learning. If we just do self-bootstrapping, roll outs, and keep the successful one, it will not work in our case. Yeah, and I think in practice, people do this by manually adding noise during the rollout, for self-bootstrapping.
And so just to clarify, so when you say human data in the middle, like you're talking about maybe 20 episodes of high quality teleop data, and then you
it's actually 50 trajectories, 50 episodes. Yeah.
50 episodes on the specific task. So if that you have 60% of 90, that means you do it for, I don't know, roughly like 50 tasks. And then for each task, you do 50 times human demo, basically. And then you do SFT, and then you get the plot in the middle, basically.
Yeah. And the human demo is provided by the UT Austin team. Yeah, it's standardized. Let's skip this confusing figure.
Yeah.
Although I'm quite proud of the presentation, but yeah, maybe I should minimize the effort for reading this.
It's a very striking figure. It looks cool. It's a great one to put up on a slide, I think.
Okay.
Yeah.
Yeah, and we also have another finding about the generalization capability. So here is another confusing figure because there are a lot of benchmarks for liberal. There's liberal Go and liberal 90, and liberal Go is has 10 tasks that's for those like articulation, pick and place, and liberal 90 is like generalization evaluation one. So for this task, we just feed the prompt of 10 tasks of liberal Go and 90 tasks of liberal 90 to GPT. And we ask, can you identify 3 tasks from liberal Go that is correlated to the task in liberal 90? So so GPT just select these 3 tasks from liberal Go and these 4 tasks from liberal 90. So here you can actually see the prompt. For example, open the middle drawer of the cabinet or open the top drawer of the cabinet. They are actually quite similar, but they are different in the background, in the scene and layouts. So what we want to do is we just do RL training and the data collection on these 3 tasks. Just few shots generalized to the these 4 in liberal 90. So if that works, then we can argue that if we want to deploy our model to have very good success rate, 100 tasks, maybe we just only need to like identify some of them, like maybe 10 of the tasks, and do the learning. That would be very efficient. And here we actually find the scaling law, like sort of the scaling law in this setup. So we only train RL and collect data on these liberal Go tasks and evaluate on the liberal 90 tasks. We can say as the data of liberal Go task increases, the performance of liberal 90 tasks also increases by using the PLD data. That is very interesting result. And you can see for the RL data, because the trajectory diversity is low, it actually cannot scale as I further increase the data size. And for the base policy rollout data, that is self bootstrapping, the performance just drop. Yeah, that's one of the
okay.
Yeah. This is one of the most interesting findings.
So the idea being that basically by identifying tasks that are very close but not similar, you can show that you can practice at those and then get good at the target tasks. That's the okay.
Yeah.
Can I ask? So this is a bit of a tangent, but it's distracting me. So like, what's up with the choice of your base models? So here you've got Octo. The previous one you had Pi 0. I think on the RL, like the real one is Groot, right? So why are they all different?
So actually, this is related to the code base. Because for simpler they have Octo and OpenVLA implemented, okay. So we just call it API. Yeah, but this should be very policy agnostic, and we will report the results of Groot later.
I'm always curious about how these models compare, I guess, is part of Sorry. So it's hard to find a real head-to-head comparison. So it's interesting that you have all of them, but not on the same chart. Sorry, that's okay.
Yeah, we have very good code base, and I will open source later, because for our code base, we can just change the base model by just like one command line code. Yeah.
Awesome. Okay. Sorry.
No, I was just gonna say it's maybe more like a feature than that. Yeah, like what Wenli just said, you can easily swap the base model and then do the residual policy. I'm still a bit wondering, like, how does the model know like what is failure? You know, especially you have the I think your probe step, right? Your hybrid data. So could you elaborate a little bit more? Like how does the policy to decide, okay, this is the time I should take over? I think you mentioned somewhere that, you mentioned kind of just now that you want to choose smaller initial action scale so that, your RL won't go and sabotage your base policy performance, things like that. But I'm just curious, like how does a policy know when this is failure and then, I should go over?
Oh, shoot. So here, the important assumption is the base model is good enough, and the optimal policy is like be bounded by a tube around the base model distribution. And here for the probing state, we don't let the model decide when to take over. We just like which is a failure state, which is a good state. We just want the policy can always take over, no matter whether it's whether it's optimal or not. In practice, when implementing the probing state, we just randomly decide whether to take over or not.
Oh, I see. You mentioned somewhere that you randomize initial state distribution
Yeah.
via the base
Here.
policy rollout. Can you talk a bit about that? You say
yeah.
something
Well,
about
I
skipping the
actually have-
scheduler.
Yeah, I
Retain
actually
this.
have a visualization.
Yeah.
I open a bottle cap by rotating counterclockwise, and now we're watching it.
Okay, so maybe the round is not synchronized.
Okay. What's it actually doing here? Oh, it's putting something in the drawer. Okay.
Yeah, and you can see this is actually nearly no probing, and the distribution is concentrated, and this is like a lot of randomization. Maybe you can see, you can see. You can see the trajectory is like it's diverged in the first second of the rollout, and then converge to the cabinet. That is the base model may make mistakes.
So I guess so you're leveraging like the base model's mistakes to get the right data distribution. And I guess it's if the base model didn't make enough mistakes, you just wouldn't need to do this. So that's fine. Is there any other like weakness to this or?
Yeah, because everything in those tasks are recoverable. So so any state of the trajectory, we will have an optimal policy that can drive back to the successful state.
If it was
That's
really
our
bad,
assumption. Yeah.
If it was really bad, it couldn't, right? Like if it was like,
if
it
it's
could like
really
knock
bad,
that
it
bowl off the
couldn't.
table, but like I guess that's the whole point is that doesn't happen.
Yeah. Because of the base policy is trained by mimicking human demonstration. So there shouldn't be very, very bad behavior like throwing away the ball because you never seen that before. So I think the most of the failure cases are coming from the precision issue. That is for those like grasping or like putting in insertion task, the base policy is not precise enough. So we can just use RL to do some correction in key steps. And we didn't like intentionally incentivize like where to take control. I think because we are using binary reward, and the RL will learn the most efficient, most optimal one to do that, and it resulted in the behavior that only take control at certain step and keeps outputting 0 in the remaining steps.
Okay, so you do have something like discount so that it is penalized for taking forever to accomplish the task. But
Yeah,
otherwise
I
it's
have
just a binary reward.
regularization term.
Okay, yeah. And so I guess so. One of the assumptions. I'm sorry. We started this because Michael had some question. Am I interrupting?
No,
But-
I mean,
okay,
yeah,
sorry.
go on, Chris.
But I was
Did I answer the question?
Yeah, I think so. Yeah, Chris, you can.
sorry.
You
Yeah,
have a
sorry. I
question?
just totally forgot. But yeah, this fund is very interesting. So this is why I keep asking things. But like, okay, so you have so one of the big underlying assumptions here is that the base model has some like reasonable level of performance, because otherwise you wouldn't be able to do your RL right at all.
Yeah.
And
yeah.
like, so I was wondering, and also otherwise the residual stuff wouldn't work, etc. So do you have any idea how good it needs to be for a new task? Like,
You mean the base
how
model
good,
performance?
how good do you need a base model to get before you can start using PLD? I guess.
So for this paper, we haven't done that ablation, but it's required by a reviewer. So
Okay.
we will run experiments and report it later. But from my experience, the base model performance is actually very tricky. So it needs to be very good. So for those GPU insertion tasks, the base model performance need to be at least like 80 to 90% success rate. It needs to know how to navigate, how to pick up the GPU and navigate to the position near the slot. And so for the real world experiment at the very beginning, I thought I overlooked the importance of the base model. I used a very simple MLP based BC policy. I just let the MLP to output the chunk, the action chunk. It's a 1D vector of like chunk size times action dimension. And I used L2 loss to train the BC policy. And the performance is really bad. It's near zero. And I thought if I learn RL for like enough time, it will actually learn. But in reality, I couldn't do that. It just doesn't work. So I switched back to SAT model, and then the success rate is higher. And then I switched back to the VLA model to use Pi 0. And now after that, I can train very good policy.
Sense.
So yeah. I think that is an insight from this project. That is maybe for now we are still not there for real world RL.
So
we need to put the base model is not good enough. So if we want to train a like policy to achieve 99% success rate, we need to put most of the budget in the base model part. And after that, we can just with little effort, RL will work.
And it basically needs to be close enough that you can just like those tiny little nudges we saw earlier are enough to make it succeed, right? Which is so very good, very close. Okay.
Yeah. So if I can do this again, I will for the 8 hours, I will spend 6 hours like collect human data and fine tune the policy, and it's 2 hours to do online RL.
So that 8 hours was all Pi 0 though. It wasn't.
I did collect some human data to warm up, to do SFT, warm up Pi, because I don't think there's insertion task in Pi pre-training data set.
Yeah, so maybe Wenli, like let me just put this in maybe more layman understanding of this, why this is still interesting. There will be some tasks where the base model, let's say Pi 0, could already be 80-90%. And in those cases, PLD can really shine because you don't need to add another human to collect sample. You just let the thing run.
Yeah.
This PLD thing run kind of autonomously. What strikes me is that you mentioned a couple of points here and there that you is like you're trying to minimize the exploration of this RL so that it don't so-called sabotage the underlying. Let it explore a little bit. Don't go too much out of distribution, and then give it enough time. It should have something that get close to like 90%, maybe even 100% in some tasks. And because that part doesn't have human in the loop, so it's great, right? You press one button, you come back 8 hours later, this thing may be 99%, maybe from 90 to 99%, right? But then what you also say is if the base model for this particular task is still pretty shit, is 60%, maybe you should just collect a lot more data, probably human data, get that particular task to edit 80-90% first before you even use something like PLD. Yeah. Am I right to say that? Basically, that's characterization. Okay, got it. I see. Yeah.
I think that's also a common sense in RL community, because for all the reinforcement learning algorithm that works in the real world, it needs very good prior. I mean, like for example, for those humanoid whole body control stuff, the prior is the simulator, the system ID, and the like human insights in reward designing. And what RL did is just interact with the simulation and distill a good policy that can be deployed. And for the LLM region, if you don't have a very good base model, RL will still doesn't work. Yeah. So I think for this real world RL stuff, it's the same. We need a very good base model to make it actually work.
Yeah. I mean, it strikes me as a trade-off between like exploration versus you explore so much that you get into a state that you completely fail, you can never recover by the base model, then you're stuck. Then you're still a human to come and repair stuff. And that's why I guess my first question and Chris' first question is, how many GPUs did you break? Because but it sounds like you didn't break any, which means I guess the insight there maybe just that the base model is actually already pretty decent. But then instead of having even more human hours to get that, you may just do this PLD thing, have it explore real world RL and get it much closer to the 99%, success rate.
I think human is needed in the cycle because you need to reset for the policy at an early stage, and also no GPU is being hurt because I'm intervening. I'm cutting it off when there's dangerous behavior.
So it's fair to say this is fairly labor intensive. This is just this is like a replacement for, not a replacement for, but like learning for demonstration can't get you to 100% performance. And this can. Is that a fair summary or of your takeaway, or no? Like this is in a way like very, again, human intensive.
I don't think I'm not sure whether it's fair comparison, but
okay.
I think there will be a long tail issue. That is, if you take the x-axis as a success rate and y-axis as a data you need, like for imitation learning, for like collect data with like learning from human demonstration, there's a long tail issue. Like as you if you want to increase from 90% to from 95% to 99%, you need way much more data than what you need from 0% to 90%. But I think online RL can close the gap by just self-practicing.
How about like longer horizon tasks? Do you think, or maybe it still ties back to the same idea, if your base model is good enough for even those long horizon tasks, then presumably
I think for long horizon tasks, most of the tasks can be decomposed into short horizon tasks. And our idea is to do the decomposition. And for the long horizon task, for example, if you are doing mobile manipulation for those navigation part, or like when you already grab the object, you just move forward and take turns. And I think those are pretty easy for the base model. You don't need to learn those skills. So we just identify the bottleneck and do real world RL and distill the skill back to the generalist. And the VLA can do the stitching and the planning stuff and perform long horizon. So I think we don't need to put that burden on RL. Yeah, and actually in our paper we have study about that. Yeah, we have this short to long generalization because there's liberal long benchmark in the liberal benchmark liberal data set. And we just learn the short-term task and deploy directly on the long-term. And you can see we are actually having pretty good success rate compared to other baselines. Yeah. And yeah. Does that answer your question?
Yeah. It does. Basically, what you're saying is that, basically online RL, like, or real world RL, you can just focus on the more atomic tasks. And if you can get those to nearly 100%, then long horizon is just a sequence of short horizon tasks anyway. And if you get good at each of the short horizon tasks, the VLA can do the long horizon planning and then stitch all these together. And you still end up getting nearly 100% of the so-called long horizon tasks. Yeah, that makes sense.
Yeah, so for the GPU insertion task, you can see once plug the GPU in this third slot, it didn't actually insert it in. So for this, I just collected 20 human trajectories, and it can do this insertion, like firm insertion at 100% success rate. It's super easy for BC. And also for this unplugged GPU from the motherboard to the table, it can also achieve 100% success rate. So for this, we don't. It's really first of all, it's really hard for RL. How can you define reward for this handover and like unplugged thing? Like you need to really carefully define the position you grasp the GPU. But for BC, it's super easy. So I think for many long horizon tasks, we only need to learn the most challenging part with RL.
Makes sense.
I was going to ask, if you were given maybe a couple more months to work on this paper, what would you have loved to squeeze into this paper? Any other application studies or things that you would have loved to try? but just ran out of time?
If I have more time and more resources, I think I'd like to compare with try also. So currently I'm using off policy RL like SAC, but I used high UTD ratio to make it more like on policy. So I'm pretty interested in try on policy RL directly, like PPO. Maybe I can build a parallel real world environment to do that. Yeah.
That sounds like a different paper already. More than just a couple of months. Okay, cool. Yeah, no, that's cool. Still cool. Yeah. Yeah, I guess maybe I don't know, Chris. You have more questions. I mean, I thought I was. I was very excited about this talking to you, Wenli. Like, I thought that any research direction that basically can do some of this autonomous learning in the real world, I think it's a great direction to have. And yeah, I was very excited by this result. Where I mean, even given the limitation that you say, I think it's still great. I mean, what you're saying is that you get a base model that's nearly 80-90% good enough for a task, and then you basically can do something like this and get it to the last 10%, because like you said, the last 10% is still a huge amount of data collected if you use a human. But if you can do the last 10% autonomously, it's a huge saving. I mean, it's not fully autonomously like you say, at least now, but this is definitely in the right direction of things.
It is a much lighter touch. Like one person could look at like multiple setups or something. I think it's probably a no.
Oh yeah, pressing a kill switch versus like doing full teleop. It's a lot easier for the humans too. Yeah. It's true. Yeah.
Yeah, you could definitely like scroll Twitter while doing it pretty easily.
Just go Twitter. Of course. Cool. Yeah, Chris, you have more questions?
No, I thought it was just really cool stuff. Really exciting. Like I think that being able to get robots to be more reliable is like one of the big things is missing, right? Like, we got to make robots reliable for them to be useful, and I thought this is really learned a lot of cool stuff in here.
Yeah, maybe Wenli, as a final question, we typically ask like any particular paper that you came across recently that you thought was really cool, you want to give a shout out to?
I think the RL100 paper is cool.
Yeah.
Are you gonna invite it off?
I think so. Yeah, I think we schedule something. Yeah.
Soon. Yeah.
I mean, that the 100 part is all definitely attention grabbing. It's like, oh gosh, 100. Yeah. That's true. Yeah, along the same vein, I would say like a goal, right? Trying to get RL to plug the get the final mile, if you will.
Can you also invite the generalist people to the podcast?
Oh yeah, we'll try. Right?
We tried. We'll
try. We'd love to. Yeah, if you are someone from journalists, please ping me and Chris. We'd love to have you guys. Yeah, very impressive videos. We'd love to find out more what they did there, for sure. Yeah, interesting. Cause like you do a lot of this, like I guess wrist camera stuff, right? I can imagine why you interested in that type of approach. Maybe more than the 3 months. The question I asked as a big like future work kind of thing. How far do you think this paradigm can stretch? What you're doing here? Maybe you do online RL, so the offline RL to online RL. Like can it start to generalize, as you kind of alluded to a little bit, to maybe not the exact same task, but like adjacently similar tasks? Because the more you can do it, then the more savings there is. Like basically, you just reduce the amount of data that you need to collect by teleop, right? What would you say is how much would you say you can push this paradigm?
We're doing some cool stuff right now.
Okay.
Yeah.
Cool.
See you in 3 months.
Awesome. Okay, can't wait. Yeah. Obviously. Yeah. I mean, yeah. That makes. Yeah. I think from my point of view, again, like I feel that teleop data probably will always be needed to bootstrap a bit, but it's so just painful to do it.
Yeah.
So if you can plug the gap with other stuff, like I really like this kind of like real world RL because it's mixed. I feel that a lot of things it's very hard to replace doing things in the real world, but you can just kind of like how a baby learn. You learn something and then you build upon previous example. You're still constantly learning, but you have a better and better base over time and just add on to it. So you don't have to keep on collecting, like pick up a new phone. I don't have to practice like 50 times every time I buy a new phone.
Like this does feel very much we're being very fluffy now, but I feel like this does feel very analogous to how people learn, right? Like you practice like one skill over and over again, then you take all the data from that and throw it back into the mixture, right? Sorry, go ahead. Yeah.
But I think like this kind of real world fast learning is what everyone was looking for. But I think for now, like all the existing method that actually works doesn't follow this. Like this is a very great hope from people, but maybe eventually there will be like real world adapting agents or like models, but it may not be adapting the weights. Maybe it comes from like adapting the memory or other mechanism. So I'm looking forward to that, but I'm not sure whether reinforcement learning is a right pathway toward that.
Yeah, fair enough. For sure. I guess I don't mean specifically RL, but I mean just some kind of continual learning, or you know, it could even be just a very big context window that you know. I'm just thinking of I mean, we humans or animals generally learn this way, right?
Yeah.
We don't need millions of like, you know, episodes. We just keep learning and then slowly update. I mean, continue to update whatever the existing model, and then just go do it ongoing continuously. Never stop learning, and then bit by bit. Anyway, you really cool work, Wenli. Thanks so much for coming.
Thank you.
And sounds like you have something already cooking up. So maybe see you in 3 months. when
Yeah.
you publish the next
Thank
one.
you. Thanks
Yeah.
for having me.
Yeah. All right. Cool.
Okay.
All right. Thank you so much. Well, we'll see you next time, I guess.
Okay.
Bye.
Bye bye.